Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study and solve some of the problems on Macaulay's method. So far, we have covered double integration method, and the methodology of Macaulay's method was discussed in the previous sessions. The course outcome and Bloom's taxonomy related to this topic is course outcome number 4, and Bloom's taxonomy level related to apply level. Now here, in double integration method, we discussed in previous sessions what is double integration method and what is the methodology of Macaulay's method. In Macaulay's method also, we'll use double integration. So Macaulay's method involves double integration, but here in Macaulay's method, we have to find out the reactions at the supports, and we have to take the section in such a way that section distance from x, distance from support, left support, at a distance of x, such a way that that equation, bending moment, that moment equation involves or considers the span of the beam, all the span of the beams, and that equation partitioned by dotted lines such a way that each partition indicates for a particular span of the beam of the slope and deflection can be calculated from that equation. Now we can understand better through problem solving the methodology of methodology of Macaulay's. Let us begin one of the problem. Here the problem is related to overhanging beam. So having a length of support here points A, B, C, where A and B are supports, and where the point C is the point concentrated load is acting at the right end, right support free end. From the right support is the 3 meters distance, 10 kilonewtons is acting at point C. The span of the beam is 9 meters, and here between two supports the span is 6 meters, and from right support to the concentrated load is 3 meters. So first is that we have to apply the concepts of shear force and bending moment diagrams, and calculate the reactions at the supports A and B, that is RE and RB, to be calculated by using the shear force and bending moment sign conventions. Now here an overhanging beam ABC is loaded as shown in figure. Find the slopes over each support. Find the slopes over each support and at the right end. Find also the maximum upward deflection between supports and the deflection at the right end. Take the value of modulus of elasticity is here 2 into 10 power 5 Newton per square millimeter, and second moment of area is 5 times 10 power 8 millimeter per 4. Now the point load is 10 kilonewtons, converted into newtons, that is 10,000 newtons. The value of the modulus of elasticity is equal to 2 into 10 power 5 Newton per square millimeter, and the value of second moment of area is 5 times 10 power 8 millimeter per 4, and we have to calculate the reactions. For that, the sum of more reactions, upward reactions, RA and RB, RA plus RB equal to 10 kilonewtons, 10,000 newtons is the equation 1, and we have to take moments about A, that is RB into 6, that RB into 6 about A, RB into 6 equal to, in counterclockwise movements, equal to, and clockwise movements 10 into 10 kilonewtons into 9, 10 into 9. So the reaction at B comes in the units of kilonewtons, that is 15 kilonewtons, and RA, that is negative 5 kilonewtons. So negative 5 kilonewtons means instead of the reaction acting upwards, that means the reaction acting downwards, that is negative 5 kilonewtons at A. That means only one reaction it is acting upwards, that is RB, that is 15 kilonewtons is acting upwards. So total load RA is -5 and RB is 15 kilonewtons. Oh, here, yeah. So that's why 10 plus 5, both are downwards 15. So RB is the main support. It is acting upwards. It is supporting for both the loads. So even though we are considering here overhanging beam where the load is acting 10 kilonewtons at the free end, by physical examination, we think that this 10 kilonewtons is carried by supports A and B. But after calculating the reactions, we got to know that only one support is carrying the entire load. That is not only 10 kilonewtons. This RA is also acting downwards. That's why 15 kilonewtons is being supported by reaction, that is support B. So in this manner, this calculations helps to understand the physical phenomenon of the load's action on the supports. Now, after that, what to do? We have to consider a distance at any section from support A. That is, we consider here EI equal EI times d square y by dx square. That is the moment equation at any section. That is EI times d square y by dx square. We already know. So that moment equation we are carrying at any section x. That is EI times d square y by dx square equal to minus RA times x plus RB times x minus 6. We consider the distance x from support A such a way that x minus 6 here at supports RA into x minus RA into say x and RA into x minus 6. Yes, we consider that means RA into 6 support at here distance x such a way that the portions A to B and B to C also covered. Now the RA is calculated as 5 kilonewtons, that is minus 5x plus 15 times x minus 6. Now if we integrate this equation, EI times d square y by dx square, that is negative 5 times x plus positive 15 times x minus 6. If we integrate once, that equation is transformed to the slope equation, that is EI times dy by dx equal to minus 5 by 2 times x square plus c1. This constant of integration to be added to the first portion plus 15 times x minus 6 whole square by 2. Now this constant of integration can be calculated by using the boundary condition. Now again by integrating the equation 1, the equation 1 is transformed to deflection equation, that is EI times y equal to minus 5 by 2 times x cube by 3 plus c1x plus c2 and plus 15 by 2 x minus 6 whole cube by 3. Now here that is minus 5 by 2 times 3, that is 6, minus 5 by 6 x cube plus c1x plus c2 plus 5 by 2, because it is the 5 times 15 and 3 cancelled at 5 times. Now the 3 cancels, 15 is cancelled by 3 by 5 times, that 5 by 2 x minus 6 whole cube. This EI times y. In the deflection equation there are two constants of integration, and in the slope equation there is one constant of integration. How many constant of integrations here? C1 and C2. The two constant of integrations which are going to be calculated by using boundary conditions. Yeah, what are the boundary conditions here? The boundary condition 1 is x equal to 0 and y equal to 0 at x equal to 6 meters and y equal to 0. At x equal to 0 meters, that means length of the beam. At x equal to 0 meters, that deflection is 0. And also deflection is 0 at another support. That's what at x equal to 6 meters. That is the span of the beam between two supports. That is x equal to 6 meters. So the slope also, the deflection is 0. So by using these two boundary conditions, let us substitute. Where to substitute? In what equation? Yeah, the deflection equation, you have to substitute these two boundary conditions. There are two unknowns as two boundary conditions. So we can calculate two boundary conditions C1 and C2. Okay, substituting x equal to 0 and y equal to 0 in equation 2, the constant of integration 2 becomes 0. Next, substituting another secondary boundary condition, that is x equal to 6 meters and y equal to 0 in equation 2, up to, that is the dotted lines, up to what portion we have to consider? We have to consider x equal to 6 meters, that is, okay, up to dot lies in the first part AB of the beam. We consider the first part of the beam, then it becomes C1 equal to 30. Substitute the C1 equal to 30 and C2 equal to 0 in equation 1 and 2. Then the equations are, one is slope equation and another one is deflection equation. Alright, these are 3 and 4 equations are very important. You can calculate the deflection and slope at any distance of x. If you substitute x equal to 0, yes, then the slope becomes 30 by EI. Then if you substitute the deflection, if x equal to 0, if you substitute in the equation x equal to 0, what is the deflection at x equal to 0? Yes, we can derive here by using at a various length, various span of values of length of the beam. Then we can derive or we can calculate the slope and the deflections of simply supported beam or overhanging beam. Now substituting, now first objective, slope over the support A. What is the slope over the support A? Substitute x equal to 0 in the slope equation, that is EI times, which portion you have to consider? First portion. Okay, we get the slope, that is between part AB of the beam, part AB, that is the first portion. What is the first portion of the beam? Minus 5 by 2. First portion, this is the first portion you have to consider up to AB. We want the total A to C, 2 portions, sum of 2 total equation to be considered. Now in the first portion, if you substitute, that is 30 kilonewtons meter square, it is in kilonewton meter square, convert into Newton millimeter square, then it is 30 kilonewton, 1 kilonewton, 1000 newtons, 30,000 meter square, that is 1000 millimeters. 1 meter equal to 1000 millimeters. 1 kilonewton equal to 1000 newtons. Because E and I are in the units of Newton per square millimeter and I unit is millimeter per 4. To maintain the dimensional homogeneity, we have to maintain, dimension. We have converted this kilonewtons and meters into newtons and millimeters. That is 30 times 10 power 9. That is theta A equal to 30 into 10 power 9 by EI. 30 into 10 power 9 by E means what? 2 into 10 power 5. I value 5 into 10 power 8. Substitute. After substituting, we'll get a theta A, that is 0.003 radians. Okay, that is 0.003 radians value. And next, we have to find out the slope at the support B. Slope at the support B, that means again consider x equal to 6 meters. The slope at support B, x equal to 6 meters. Substitute in the slope equation here, EI times in the first portion, this AP related to first portion and AC means first and second portions completely, we have to substitute. Now EI into dy by dx, at P, then the equation minus 5 by 2 times x square plus 30. Alright, in that equation what to be substituted here at x equal to, that is theta B at a distance of 6 meters from left support, that is minus 5 by 2 times x, that is 6 square plus 30. Then it becomes minus 90 plus 30 minus 60. Convert into that kilonewton meter square into Newton millimeter square, that is 60 times 10 power 9 Newton millimeter square. And EI substitute here, that is theta B equal to minus negative value of 60 times 10 power 9 by EI. What is the value of the E? Modulus of elasticity is E into 2 into 10 power 5 and I is 5 into 10 power 8. After substitution, you will get it, that is negative value of 0.006 radians, theta B. So the slope at A, it is positive, upward, and slope at B, it is negative. Alright. Now, what is the third objective? The third objective in this session is slope at the right end. Slope at the right end, that is at C. We want at E. Then what is the slope? We want theta. Theta C. Theta C is where it is. Here, overhanging beam. This is C, A, B. This is 6 meters. And here it is 3 meters. So at theta C, that means first portion, there are two portions in the equation. EI times dy by dx equal to minus 5 by 2 times x square plus 30 dotted line. Next, plus 15 by 2 x minus 6 square plus 15 by 2 x minus 6 whole square. So here the portion C we want, that means from left support up to C, that means first portion A to B, this AB portion, and it is B to C. So we want the total from up to C, that means A to C, we have to consider the total distance. That is a slope equation, that is at C, theta C. That's why here EI times theta C equal to minus 5 by 2. What is the x value here? 9 meters. Substitute here 9 value. 9 square plus 30 plus 15 by 2, 9 minus 6 whole square. Okay, 9 minus 6 whole square. Then, after calculating the value, here how much it is in the value in the form of kilonewton meter square. That means substitute 105 times kilonewtons, 1000 newtons. 1 meter equal to, that is again 1000 square. Then it becomes 1 is 105 times 10 power 9 Newton millimeter square. Now what is theta C? This is EI times theta C. What is the theta C? Then theta C means EI goes the denominator to the right side. Then EI. This EI is in the form of Newton square millimeter and I is in the form of millimeter per 4. That's why to maintain dimensional homogeneity we converted kilonewtons into newtons, meters into millimeters. That is, then after substitution and conversion, after conversion and substituting the EI values and also the value obtained from EI theta C, then the value obtained after calculating the slope is negative value of 0.00105 radians. So these are, in this problem we calculated only slopes at supports theta A and theta B. Okay. Now we consider up to so far we calculated the slopes at support A, at support B, and at support C. Not at support C, at the concentrated load point C. So at concentrated load the deflection is negative. But whereas at the support B also negative, but at support A it becomes a positive value. So this is the effect of deflection curve. You draw the deflection curve at support A is positive, support B and C are negative. Now we have to find out the fourth objective is that maximum upward deflection between the supports. What is upward deflection? So if you want a deflection, maximum deflection, that means the slope equal to 0. That is dy by dx should be 0. So equate dy by dx equation after substituting C1 value in that. That is equal to 0 equal to minus 5 by 2 times x square plus 30. The x value, here it is calculated 3.464 meters. Okay, 3.464 meters. Now substituting this 3.464 meters in the place of where? In the place of slope equation, deflection equation, that is Zi times y maximum equal to minus 5 by 6 times. What is the fourth equation? Equation 4. This is the equation 4. In the equation 4, what is the value of x is 3. Depends upon the value of the x value, that is 3.464. The 3.464 is in the span between what? Where it is? A, B, C. between A and B it comes. That's why we have to consider the first portion of the equation of the slope. This portion we have to consider. First portion. That's why here the deflection, the slope equation is minus 5 by 6 x cube plus 30 times x. So here this first portion we have to substitute x value. That relate because that x value comes under the portion of A to B, between A and B, points A and B, between two supports. So this one first portion equation is AB related, second portion related to BC related. For the first portion AB, alright. So based on the x value, we have to consider the part. If x value comes more than 6 meters, then you have to consider the total portion, total equation, first part and second part also. That means total equation. That means the first part is considered here. Why? The x value comes under the portion of between two supports, that is 6 meters. That is minus 5 by 6 x cube plus 30 times x. Minus y, I times y equal to minus 5 by 6. What is the value here? Minus 5 by 6 x cube plus 30 times x. So, yes, that is what we did here. Minus 5 times x cube plus 30 times x. X value 3.464. Consider only first portion. Why? The x comes under the limitation of 6 meters A to B. That's why first portion considered. Now after substituting y maximum, we got the value. That value is in terms of kilonewtons and meters. To maintain dimensional homogeneity, convert into this kilonewtons meter cube into newtons millimeter cube. Then the value becomes 69.282 times 10 power 12. Now y maximum equal to 69.282 times 10 power 12 by EI. What that E and I values are? The IE values 2 into 10 power 5 and I values are 5 times 10 power 8. Then the y maximum is 0.6928 millimeters. That means positive value. It is upward direction. Y maximum at the distance of 3.464 meters, the deflection curve become positive. Now deflection at the end, at C point. The deflection at C point means we have to consider the value of deflection, that is that equation, total portion, that is 5 by 6 times x cube plus 30 times x, then plus the equation for I times yc. The c is x equal to 9 meters, that means A to C portion. The equation in the equation of minus 5 by 6 x cube plus 30 times x plus 5 by 2 times x minus 6 whole cube. In that equation, substitute x value. Then y consider this is the first portion actually in the equation. This is the second portion. Why? Because x is related to throughout the span. For throughout the span, this is the equation. If x equal to 6 meters, up to 6 meters, first portion considered, then more than 6. First plus second portion to be considered. Now in that x, in the place of x, substitute 9 meters. 5 by 6 times 9 cube plus 30 times x plus 5 by 2 times x minus 6 whole cube. Now this is 270 times 10 power 12 Newton millimeter cube. What is the yc? EI times yc equal to minus 270 times 10 power 12. Now what is the yc? Minus 270 times 10 power 12 by EI. What is the value of the E? 2 into 10 power 5. What is the value of the I? 5 into 10 power 8. Then the YC comes my negative of 2.7 millimeters. This is downwards. At a YC it is downwards. Y maximum. Yeah, it is so peculiar. We consider here. If you draw this deflection equation, deflection curve. Yeah. With the reactions, this is 10 kilonewtons acting. In that equation we write down, yes, 10 kilonewtons. At x equal to 3.464 meters, this is 6 meters and here it is 3 meters. Point A, B and C. At 3.464 meters, at this point, at the x value 3.464 meters, the maximum value is 0.6928 meters. Point 6928 meters, and at y maximum, and at point C it is negative 2.9 meters. This is the curve deflecting, because the deflection at supports x equal to 0 and x equal to c, if we substitute, that becomes, the portion becomes yes. Now this is the manner it is deflected. Here negative, negative, and here it is the positive. The positive value here it is how much? 0.6928 millimeters, 0.6 millimeters, and here it is 2.7 millimeters. Okay, so this problem is so important. In this problem we used Macaulay's method for your overhanging beam and calculated the deflections, maximum deflection, and also location of the maximum deflection, and we found the deflection value at the concentrated load, and also slopes at the supports A and supports B, and also point load at where the load is acting, concentrated load at that point, that is point C. So total 5 objectives are calculated in this model, in this problem of a overhanging beam. Then if we consider the second problem, in this problem, yes, it is also overhanging beam, but the overhanging beam for this, but here it is overhanging beam, but having a combination of 2 loads. One is concentrated load, another one is UDL, uniformly distributed load. The uniformly distributed load here acting in the portion between D to B, and the between 2 supports A, B, the length of the beam is 6 meters, and 10 kilonewtons is acting from right support at a distance of 3 meters at point C. Now let me read the problem here. A beam ABC of length 9 meters has one support of left end and other support is at a distance of 6 meters from the left end. The beam carries a point load of 12 kilonewtons, here 1 kilonewton given here at the right end, and also carries a uniformly distributed load, the 12 kilonewtons at the right end, and also carries a uniformly distributed load, yes, 4 kilonewtons per meter, the uniformly distributed load, over a length of 3 meters is shown in figure. Determine the slope and deflection at point C. Determine the slope and deflection at point C. Take modulus of elasticity value for this beam is 2 times 10 power 5 Newton per square millimeter, and second moment of area value is 5 times 10 power 8 millimeter per 4. How to calculate? By using here Macaulay's method. Here they did not mention anything which method, but for this type of problems, in order to avoid complexity, we have to use Macaulay's method. It's so important, it's so simple to calculate anywhere. Now we have to, first of all, what to be found? The first step, while solving the problems, this type of problems, we have to start taking first. What is the first step? The first step is calculate the reactions at the supports, here in this case RA and RB, by using the concepts of SFD and BMD, shear force and bending moment diagrams. Second step, take the equation or write down the equation of bending moment equation by considering a distance of x at a certain portion between B and C here in this case, such a way that all portion that equation consists of throughout the span of the beam x value. So now in this case, what is the second step? Calculate the bending moment equation at a section x. Consider the distance x from left support A to points between B and C. Between B and C points. And equate that equation with the equation of, again, section at x, that is E times d square y by dx square. What is the fourth step? The fourth step is that integrate the above momentum equation once. Then it comes slope equation. Then fifth step comes deflection equation. The deflection equation is integrating the slope equation. Then this deflection equation consists of constant of integrations, two constants of integrations. Those two constants of integrations are to be calculated by using two boundary conditions. After calculating those two constants of integration, we have to substitute back in the slope and deflection equations. Those equations are generic equations of slope and deflection. In that, we have to substitute the values of different values of the x. In the deflection equation, if you substitute different values of x, and deflection values can be calculated at particular distances. Similarly, in the slope equation also, if you substitute the values of x equal to 0, x equal to 4 meters, x equal to 6 meters, but provided we have to, after doing this momentum equation or deriving the deflection slope equations, here there are two partitions will be there, two parts. One partition, two parts. First partition is related to the portion A to B, and sum of first and second related to toward the span AC. Alright, how to start the problem? Yes, first you have to calculate the reactions. That is point load W equal to 12 kilonewtons. Uniformly distributed load, that is 4 kilonewtons per meter. And E, modulus of elasticity 2 into 10 power 5 Newton per square millimeter, and I value 5 into 10 power 8 millimeter per 4. Calculate the reactions at A and B. The total load, what is the total load? Equal to RA plus RB, upward reactions equal to total load 4 into 3, 12 kilonewtons and 12. This is 24 kilonewtons. That is equation 1. Next, take moments about A, that is sigma MA equal to 0, that is RB times 6 equal to 4 into 3, that is total load 12 acts at a midpoint, that is 1.5 plus 1.5 plus this distance 3 plus 1.5 4.5 plus 12 into 9 6 plus 3 9 meters. This is 162. So RB value is 12 kilonewtons. Now the total load, then RA equal to total load minus RB. The total load is 24 kilonewtons minus 27, that is negative 3 kilonewtons. So at RA, the downward reaction is not upward, it is negative. So downwards, it is acting downwards. Then after substituting those reaction supports, we have to draw the diagram. We have drawn, that is RA is 3 kilonewtons acting downwards. RB is 27 kilonewtons acting upwards, and here it is 12 kilonewtons acting downwards. So here the portion between B and C, we are considering UDL, that is 4 kilonewton meter upwards, and also another UDL upwards, another UDL downwards, the top and bottom. So it will be cancelled, no effect. For our simplification, in order to find out the UDL at the same time, because UDL up to some portion, if it is complete portion, if we consider, and it can be useful for both the cases. Now, For that equation, the distance at the support we consider from support A between B to C portion. Then it becomes what? RA times X. RA times X, negative times, here negative RA we kept here, that's why, otherwise positive RA. RA times X plus negative of, here downwards, negative 4 minus X minus 3 into X minus 3 by 2 plus RB times, how much X portion? This is X minus 6. This is the total portion X. X minus 6 plus 4 times X minus 6 into X minus 6 by 2. Now, RA, substituting RA value and simplifying, this is EI times d square y by dx square. Okay. Now, substitute here the value of dy. Substitute here the value of d. Yes, this is the equation, bending moment equation. If you integrate once, first bending moment dy by dx, first integration dy by dx, that gives the slope equation with C1, and integrating the slope equation, you will get this deflection equation with two constants of integration C1 and C2. EI. Yes, these are the equations. This is the slope equation. It is a deflection equation. So the deflection equation 1 and 2 are slope and deflection equations, but that slope equation 1 consists of one constant of integration C1, equation 2 consists of two constants of integration C1 and C2. Okay, now these two values are to be considered, are to be calculated by using two boundary conditions C1 and C2. What are the two boundary conditions are? At x equal to 0 and y equal to 0, at x equal to 6, another support, and y equal to 0. The deflection, the slope, the deflection is 0 at the supports. There is no deflection. That's why the boundary conditions we are considering here at the supports. So x equal to 0 distance meters, the slope deflection is 0. That is the support A. And x equal to 6 meters, again the deflection is 0. That is support B. So by using these two boundary conditions, but where to substitute? Because these are the slope equations, slope value, deflection value, so we have to substitute in equation 2. So after substituting equation 2, we observe here, always maximum it comes here, the C2 becomes 0. So with what portion you have to consider? At x equal to 0, that means it is the portion between A to B. That first portion you have to consider, first portion of the equation. What is the first portion of? Yes, minus x cube by 2 plus C1x plus C2. This is the first portion for the first boundary condition. For second boundary condition, x equal to 6, up to what portion? You have to consider such a way that up to here. That's what happened here. Now C1 value 20.2425, C2 value 0. Substitute this C1 and the C2 in equation 2 and equation 1. We will get the final slope and deflection equations. Now, if we substitute x value less than 6 meters, we have to consider the first portion. After the 6 meters, you have to consider toward the portions here, toward the length. Up to AD. Yes. Now, slope at point C we want. What is the slope at point C? It is at a distance of 9 meters. Substitute in the slope equation. 9 meters means throughout the equation. Then theta C obtained. The theta C here, EI times theta C equal to minus 105.75 into 10 power 9 Newton millimeter square by EI. That is EI value. That is negative of 0.001057.5 radians. Then, what is the deflection at point C? EIYC. We want at C. Again, through the equation. Substitute x equal to 9 meters. The value is observed as 2.6325 millimeters. So, in this manner, we have to consider the different equations, deflections here. So, we solved two problems in this session which are unique, by using especially in the Macaulay's method. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.